So you should have two things in front of you right now. You should have these notes, and you should have this questionnaire. Where is it? Right here. Is anybody that didn't get this thing that says Space Environment 1, what you should learn from this lecture? Anybody that does not have it? Okay. The last pages on this are questions that you have to answer and turn in. So don't forget it. What I've tried to put on the first couple of pages, or the first page here, is what are the things that I think are important, and then the questions on the back. Anybody else? Okay, does everybody see that? So look at Space Environment 1. Some of this stuff you've already seen, and we want to go over to make sure you understand it. Put this in a place. If there's anything that you want to keep in your notebook to start with, this is it. Okay, because this is the real meat of the course. So we want to talk about the space environment. Okay, so how does the space environment affect your spacecraft design? What about the structure in it? Does anybody think the environment's going to affect the structure of your satellite? How will it do it?
Lots of ways.
Okay, she says lots of ways.
It's a shield for them.
Right, yeah, right. Okay, anybody else?
You have to account for how the satellite will drag upon it and other effects of the particles in the upper atmosphere.
Okay, good. How about the electronics? What's up there in the space environment that's going to affect electronics? Anything?
Solar flares.
All the radiation effects, right? Okay. What about solar panels? Does the environment affect solar panels? Yes, it does, because it degrades solar panels. When you design a satellite, if you say it's going to last for 5 years, you have to over-design your solar panels such that at the end of 5 years, it still has the amount of power that it needs. So there's end of life and beginning of life designs on the solar panel. What about the radio communications? Does the space environment affect that? What goes on periodically that affects radio communications in space? Solar flares. That little old solar flare. Okay, so we're going to consider some of these things here. Here's the thing that I think is really interesting is what is the environment up there and what is the hazard that occurs? So if you look up here, you've got cosmic rays and solar flares. Single event sets, latch-ups, interference. That's what's caused by that. Solar flares up here, radiation damage, energetic plasma charging, low energy plasma, leakage sputtering, okay? And neutral atomic oxygen, erosion on the surface of your satellite, and debris. There is a lot of debris up there, man-made and natural debris that hits your satellite. So, that chart right there is one of the very important ones. This is as equally important. Those two charts really cover everything about the space environment. So let's just look at it up here. What happens in the vacuum? They say we get UV degradation. What does that mean? What is UV? Ultraviolet. Ultraviolet up there can affect things that are there. Do you see any effects of ultraviolet here on the ground? Sunburns? That's right. What happens if you lay a newspaper outside for a while? What does it fades it. It sometimes turns it yellow. Contamination. What do you think about contamination in a vacuum? There isn't any contamination up there in the vacuum, is there? Where does it come from then? The spacecraft itself. It comes from the spacecraft itself. You send this old dirty thing up there and it outgasses and spews stuff all over the place. Okay. Neutral up there. Mechanical effects. Aerodynamic drag. Aerodynamic drag does what? It's, if you got something that's creating a drag, it's dissipating energy, right? So if you dissipate energy of a satellite in orbit, what happens to it? It deorbits, right? Okay. What about physical sputtering? Do you know what physical sputtering is? How many people here have their computer booted up on the internet? Look up sputtering. What is sputtering? It's just a little different than stuttering, right? Okay.
Sputtering is a process whereby atoms are ejected from a solid target material due to bombardment of the target by energetic particles.
Okay. So we have energetic particles up there. Back to this. Sputtering. Sputtering is like you're throwing a rock into the water and the stuff that splashes out. So if you have an energetic particle coming into your satellite, it can actually knock stuff off of the outside of it. You might have a coating on the outside of it, and it can actually knock that off. So that's one of the things that occurs up here in the neutral environment. The other thing is the chemical effects. Atomic oxygen, spacecraft glow. If you've ever seen the shuttle, when it's going along at night, you actually see it glowing. There's ionized gas around it. Plasma. What's plasma? Anybody know what plasma is? Plasma is a molecule that has an electron or a proton knocked off of it, and it has a charge. And what happens is you see, in fact, if you look up here and look at the fluorescent lights, you're looking at a plasma. What they do is they apply a potential, and they pull electrons off of the gas that's in there, and then when they combine, they put out a light. Okay, so that's plasma, and we'll talk more about that. Some of the effects of it. Radiation, we've talked about radiation before. Solar cell degradation, sensor degradation, the effects on electronics, single event upset latch-ups, and then micrometeoroids and orbital debris. Is there much orbital debris in space? At certain places around the Earth. There is the natural debris that's up there due to comets and other kinds of things, but we've been really bad about what we've done in low Earth orbit. The area between about 400 kilometers and up to maybe 1,200 kilometers, there's a lot of junk in there. And we'll talk more about that and what we do about it. You actually have to think about designing for it. Okay. Let's go down. So consider the environment. You know, one of the things that we have, unfortunately, we have the Earth's magnetic field, and it's generated by what? What's generating that magnetic field? The core in the Earth is generating it, right? The molten core in the Earth. Does it ever change? Yes. They have shown that it's actually flipped poles at some time in the past. And it's actually varied some over the last 100 years or so that it's been measured. Very smooth and well organized, right? Not very much. You know, you can see all of those lines going around there. So it isn't just like a bar magnet that you have a North Pole and a South Pole and all the lines are really smooth. One of the things that got into trouble with a satellite that I helped build a few years ago, always assumed that if you had a satellite and you put something in it so it would follow the magnetic field, we always felt, you know, when it got up to here, like at 45 degrees latitude, that you would still look out the side and see the Earth. So we put a camera in the side of it. The satellite was a box about this big and about that high, and we put the camera sticking out the side of it. Well, that was super. We were from Utah, and we wanted to see the Great Salt Lake with our satellite. But it turned out that when it got up high enough, so it was over Utah, the camera actually pointed above the horizon. it tilted really, really fast up in here, and we didn't realize it would do that. So the only place that our camera would take any pictures is over the magnetic equator, or near the Earth's equator. So we took pictures of the Philippines and all places that were near the equator, but none of what we wanted to is our own local area. Okay, so this is what happens when we have those solar flares. And all of this eruption of all of this material and radiation comes out and it bangs into the magnetic field. And what it does is it creates this area out in here. What's this area called? The magnetosphere, right? And what it does is all of this stuff floats around, it comes back, and there's a big tail out there. Fortunately, we do have the magnetic field. And here's what it looks like with the sun and some of the eruptions that are occurring. Look at these things. They go boing, and then apparently they're charged particles, and there's magnetic fields around the sun, and it just sucks them right back in. But that's a tremendous thing that we've got out there that's spewing stuff out at us. So this is very important to understand what happens when charged particles come towards the Earth and hit a magnetic field. If you have a charged particle coming in and hit a magnetic field, what does it do?
Circles around the magnetic field.
That's right. It circles around the magnetic field, and it's up in here. If you look at which way it goes, look at the angle of it up here. They got an angle like this, so if it's going this way, it'll go zoom, zoom, zoom over here. But what happens right over in here? What happens as the magnetic field gets stronger, and it does, it's going to get stronger near the poles. Actually, look at the angle that thing's at. It actually comes down here, and it gets perpendicular, and it actually reverses and goes back. So these charged particles circulate back and forth, and they don't come clear down to the Earth right there, because fortunately the magnetic field is strong enough that it actually causes them to turn around and come back. So those things don't come down close. But there's a special case here that we'll look at where they do come down pretty close. What happens to the sun? Every 11 years approximately, it has this solar cycle and spits out all of these particles. So if you want to go up in space and you want to be launched off of the off of the International Space Station, you want to go up there when you have the least amount of drag, right? You would like to stay up the longest. So what you do is you pick a time when you're in the valley there that there's the least solar flares going on that's heating up the atmosphere. And this is some things here. We'll go on a little bit more. Now, what happened when they first started flying satellites, I don't think they realized it, but they found that there are these, what's now known as the Van Allen belts. And can anybody tell me what the name of the man was that discovered that? Oh my gosh, what a smart bunch of people. Okay, so you can see there are actually two Van Allen belts, and you can see different things happen in each belt. These belts actually vary according to how much solar flares and galactic cosmic rays are coming in. In your slides, if you see something like this, you can click on it and it'll show you a whole bunch of different pictures. So I put those live links in the slides. Okay, and do you believe in aliens? They found one in Lexington, I think. Doesn't that look like Lexington to you? Okay, here's a bigger picture of showing what happens with the magnetosphere, and you can see the tail out here of it and what happens. One of the things that they really want to do is they really want to fly a whole cluster of satellites out in here, and when one of these flares hit, what they do is they want to see how the magnetosphere actually pulses. But you can see also here the Van Allen belts that are there. Okay, just another picture. You know, everybody draws a nice color picture of that one. Here's a nice one. You can see some of it. They've got satellites that are out in that area out there. Okay, see how the particles are trapped there. Okay, so what are some of the things that these solar storms do? Here's a thing that I picked up off of the internet that just talks about what happened during this period. And there's this October 23rd, 2003. And some of the names you should recognize here from that video that we had about the Earth. The spacecraft Genesis, the solar wind satellite, was at L1 and it entered a safe mode. So what is L1? Has anybody heard of L1 before? Has anybody ever heard of Lagrange points? What is a Lagrange point? Anybody? Do you know what a Lagrange point is? You're familiar, right?
I've only seen it in a science fiction novel, so
It's for real. There are, yeah.
So, according to the Wikipedia, the Lagrange points are 5 positions in an orbital configuration where a small object affected by only gravity can theoretically be part of a constant shape pattern with 2 larger objects.
Okay, you've got the Earth and you got the Moon, and there is some place between the Moon and the Earth that it goes to, the gravity pull is 0. You got just the opposite to go to 0 at some point, and that's called a Lagrange point. There is a Lagrange point between the Sun and the Earth, and I think there's actually a Lagrange point on the back side of the Earth and on the opposite side that the Moon's at. But theoretically, if you could put a spacecraft there, if it had no other perturbation, it would stay there. It's the one spot that it'd stay. But what would probably move it around? What is it that blows through? Solar winds. So even though the gravitational pull there is 0, there are other effects out there that would move you around. So this satellite is a solar wind satellite out of this Lagrange point, and it went into safe mode. What does safe mode mean? On a satellite, when all else fails in the satellite, it goes into what's called the safe mode. And in the safe mode, that is the time when it uses the least amount of power and it shuts every unnecessary thing down. It's kind of the lowest power draw point that you can get. And we're going to be talking, and you'll hear about safe modes. It means something is drastic and it goes back in this mode. It's kind of like going back into its cocoon and trying to preserve itself. So that's what happens when anomalies, and that's what you design a spacecraft to do, is when something that it doesn't know how to fix it, it goes into the safe mode. So here's airlines were rerouted due to high frequency and very high frequency communication. It means that the communication was so bad during these solar flares that they couldn't communicate with their home base. So they rerouted them so that they probably didn't go up near the North Pole or near the South Pole, so that it wasn't disturbed by that. Okay. Midori 2 is an Earth-observing satellite, failed. It was probably lost. Safe mode, power drop, telemetry dropped. Telemetry was lost, so it killed the satellite completely. Stardust Comet mission went into safe mode due to read errors, but it was recovered. Chandra, X-ray astronomy satellite, observations halted due to high radiation levels, but it was restarted. GOES 9, 10, and 12. What are the GOES satellites? Those are the satellites for weather, okay? Some of them are geostationary and some of them are actually orbiting, polar orbiting satellites. But when you see GOES, that means that they're weather satellites. So the GOES, the magnetic torquers were disabled, so problems there. Rhesus, solar satellite, had spontaneous resets on the CPU. And what you do on these satellites, if you end up with a situation, I think we talked about it before, on the little satellites we have in a thing called a watchdog timer. And you set this timer, it's like setting your alarm clock, And if the alarm clock goes clear down or goes off, then what it does is it resets your processor on your satellite, okay? And if you, but what you do to stop it from that, if everything is working right, you go back right before it reaches the time and you reset it again. So reset, reset. Oh, I'm lost. I don't know what to do. Bang, it resets your processor. So it's a way that in case something happens that it doesn't recognize, it will reset itself. And in fact, Garrett Jernigan has the little mag pocket cube to reset every 25 hours regardless. He says, I want to reset every 25 hours because I don't know what's going to happen. You'd like to get off of the cycles. You don't want things to happen on the half hour, the hour, or everything else, because if you get them off synchronous, it's easier to detect them. I think one of our satellites, we had it beaconing, and it had it beaconing every 30 seconds, and there was a real problem with it because something else happened to be on that time. In fact, it's better that you have some things that kind of go off randomly rather than really synchronize it. Okay, so we have a few more of these. Smart one, shut down of the engine due to increased radiation levels in a transfer orbit. Now that's bad. Remember we talk about, and we'll get more into it when we talk about orbits, but the way you put things up in geostationary orbit is you put them into a transfer orbit where they start out and they're in a highly elliptical orbit. It's the top up here is where you want it in geostationary, but down here at the bottom it's very close to the Earth. And the reason that they do that is normally the rockets that put them up there do not have enough power to put them all the way up to go around in geostationary orbit. So what they do is put them in what they call the geotransfer orbit, and then they have a motor that will fire down at the perigee to circularize the orbit. And so this happened in a very critical time when they were trying to circularize the orbit, that they got a flare and it got hit. Okay, Chandra observations were halted again autonomously, but they later resumed. NOAA, another weather satellite, they lost the scanner on it. GOES 8, X-ray sensor turned itself on and couldn't be recovered. Astronauts on the International Space Station went into the service module for radiation protection. The FAA issued the first alert ever on radiation doses received by airplane passengers above 25,000 feet. Let's see. Power system failure at Malmo, Sweden. That means that energy came in enough to hit the power grid to trip off breakers in the power grid. The ACE and the wind, solar wind satellites lost plasma observations. Chandra, again, well, a GOES satellite, the sensor saturated. Chandra halted again. Kodama, data relay satellites in geosynchronous went into safe mode. Signals noisy. They don't know whether they didn't know whether they recovered it or not. DMSP, that's a military communications satellite, lost data twice, recovered microwave sounder, lost oscillator, switched to redundant system. The Rhesus satellite again had 2 more spontaneous resets. CHIPS, that's a science satellite. Computer went offline and contact was lost for 18 hours. It went into a tumbling but was recovered. SOHO, that's one that they used to look at the sun at the L1, commanded safe mode for 3 days. A lot of times if you know about these storms that are coming, the thing to do is you put them into safe mode. The less power that you have on the instruments, the better off it is. Mars Odyssey spacecraft entered the safe mode. The twin Mars Explorer rovers both entered sun idle mode due to excessive star tracker events. Stable and wait for recovery. Certif, do any of these names sound familiar for the ones that we've seen in that Earth to Space movie? Some of them do to me. In orbiting, drifting behind the Earth, turned off the science experiments, went to Earth pointing due to high proton flux, 4 days of lost operation. X-ray timing satellite. Well, go ahead and read through some of those, but it's about the same thing that always happens. Here's one. The WASP service interrupted in CONUS high latitude GPS receivers. What's CONUS? Continental United States. What is WASP? WASP is a geostationary satellite that looks at the atmosphere and sends out corrections for GPS receivers. Loran C station in Newfoundland. Loran C is things that are cross country. That how many of you in here are pilots or aircraft enthusiasts? You've heard of Loran C?
Yes, but I don't know much about it.
Yeah, it's a navigation system before they got GPS. Okay, Chandra again. Okay, here, this is this thing called the South Atlantic Anomaly. Okay, over South America, if you have, here's some plots of single event upsets that have occurred, and you see there's this one point right over South America called the South American Anomaly, SAA, where that occurs. What orbit could you have that would not go through the South Atlantic Anomaly? A what?
Polar orbit?
No, wouldn't the polar orbit go through it? How about an equatorial? Right? Okay, let's see. Ta-da. Okay. Again, here's showing. What's the reason? The magnetic field of the Earth pole does not line up with the physical pole. So what happens is this is tilted, and this place down here, you remember where the charged particles turn around and go back? That's closest to the Earth right here, and that's what causes it. Everybody said, oh, well, it's due to a large iron deposit in South America and everything else, but I finally asked a friend of mine who is an astrophysicist, and he said, this is what it is. It's due to the misalignment, or not misalignment, but to the non-alignment of the magnetic field with respect to the physical field on the Earth. And so it brings this down here, and there's probably less radiation up here just due to that. But there's three places that you get radiation from the Van Allen belts. One is you get it up in here, down here, and there. Those are the three places that you get it. The reason you get it up here is the magnetic field. There are particles that come in here that are not necessarily trapped by the magnetic field. Okay, here's the Van Allen belts, two regions that trap these particles. There's the inner belt, and the inner belt is energetic protons. The outer belt is generally electrons, high energy electrons with the energy there. And what's the difference between the energy that's contained within a proton at the same velocity as an electron? Yeah, it's the thing is the mass, right? So if you have an electron zipping along and a proton zipping along, the proton's going to have a lot more energy in it, right? E equals mc squared, right? So C is the same, m is different, lots more energy. So that's why the protons tend to get into the inner belt. They're not traveling as fast. And the electrons in the outer belt. Here's an interesting thing. They're alpha particles, and later on they'll define the different kinds of particles. It's a helium atom of which it's lost two of its electrons, and it causes what they call a ring current. So you know about current in your electronic wires, right? This is a current that's in the atmosphere that up in the Van Allen belts that's floating around. So anybody have any questions on that? Okay, let's go on to the second one, and that's number 2, solar flares. Look at the amount of time here, And the solar flare comes in, and this is the atmospheric density. The solar wind comes in, and it's heating up the atmosphere. And then all of these other particles come in, and it's heating up the atmosphere further. And so that makes the density of the atmosphere more at a higher altitude, or a given altitude. It raises the density, it increases the drag. Okay, how do you know, or how can you estimate how long something is going to stay in orbit? Well, leading question on that is, how long does it take a solar flare to get from the sun to the earth? Solar flare occurs, how much time have you got? 30 minutes. 30 minutes. Starts out here, 0. The sun goes burp. Out it comes. 30 minutes later it hits it. 50 minutes later it's past it. So okay. This is the chart that I showed you, a little bit more about it. What are the effects of vacuum? Thermal control. You have no air to move the heat around. It can only be moved by two methods. What are they? In the spacecraft, there are only 2 methods with which heat can go around. Normally we talk about 3 methods. Radiation, conduction. What happened to convection? No atmosphere. Good. You've got to control internal temperatures and external temperatures. We'll get into that some more. Think about internal temperatures. What do you think is the thing inside that generates the most heat? Pardon? What? What component generates the most heat? Normally the transmitter. Right? Why the transmitter?
That's because the energy that's converted and working away is entirely converted. So
that's right. They're not 100% efficient, and that's generally the component in the satellite, at least the little ones, that consumes the most energy. Okay? Externally, what do we worry about heat externally from? What if it's down in the atmosphere starting to deorbit? Where's the heat come from? Atmospheric friction, right? What other source of heat do we have on the outside? Sun. And there's a third source, and it's the infrared radiation off of the Earth up to the satellite. So there's at least those 3 sources on the outside. How do you control the temperature on the outside? There are ways, okay? Think about this. You go outside with a black shirt on. Or, I mean, what do we do with the heat on the outside? Or how do we control it? When you go outside with a white shirt on, is that different than going outside with a black shirt? What are you experiencing?
You're absorbing more of the radiation.
That's right. There's absorption and reflection, right? Okay. So what you put on the outside of the satellite can control the temperature, outside temperature of the satellite. And controlling the outside temperature can somewhat control the inside, because where does the heat on the inside have to go to get dissipated? To the outside, right? So that's something to think about. Okay. Atmospheric drag at LEO orbits, and we'll see a little bit more of this. One of the things is in the vacuum is a lack of atmosphere to protect us from space radiation and space debris. What happens to space debris in the atmosphere? Burns up. Okay. So here's the vacuum environment. What we have to do is have a thermal balance on our satellite. You've got the Earth that has reflection and infrared radiation, so that's coming in. You've got 1,350 watts per square meter from the sun coming in, and then you've got internal heat. So what you do is you control these effects by the emissivity and the absorptivity. And they're different materials, like a white shirt and a black shirt have different characteristics. So they're paints and coatings that you can put on the outside of the satellite. What do you do about where you have solar cells? There isn't nothing you can do because you don't want to put anything over them, right?
I mean, you only put solar cells on the sides that will receive the vast majority of the sun, or at least ones that will receive sun here.
Yeah, but the thing that you want to do on the little satellites is you want to cover as much of the surface as possible with solar cells, right? To generate power for the spacecraft. Okay. UV degradation. Most ultraviolet is absorbed by the ozone, but we're above the ozone. So we need material that we can use for thermal control and is not affected by the ultraviolet. And some of that, as one of the ones that we're familiar with, is Kapton. And that's that pretty gold colored tape, right? Really quite impervious to ultraviolet light and atomic oxygen and other things. If you see a large spacecraft, they'll build actually and put on what they call thermal blankets. And the thermal blanket is a layer of Kapton, and inside is like a layer of lace. It's almost like a honeycomb with each surface area covered with Kaptons. And what they do is they have these little old ladies that know how to make quilts actually make these blankets for the spacecraft. And they get paid more than they do for making quilts. Can you imagine that? So remember that. But that's what they'll do, is they'll put blankets on around the big spacecraft at various places. We don't do that on the little spacecraft because we don't have any little ladies to make little space blankets for them, so we're out. Okay, but remember Kapton. Molecular contamination. Surfaces contaminate due to outgassing processes. The most vivid example of outgassing is a new car. How many of you smell that nice smell when you get in a new car? You smell it? Do you like that smell? Yeah. Do you ever notice what it does to your windows? Windows get dirty in a new car, inside really quick. And if you take something and clean them off, they're all black. That's what's coming out of that adhesive that they have on the material on the inside of the car. And you thought it was good, right? I like the smell of a new car too. But it's amazing how much it is. You look at it. Have you got a new car? Have you had a new car lately? No. If you get a new car, did you notice that? How dirty the inside of the windows got? And you know what? You're breathing all that stuff. You know, I'd bet you don't drive around with the windows down, do you? You do? Okay, well, we'll know we'll have you around for a few more years at least. But that's a really good example of things outgassing. One of the things that we do on satellites is do what? When we start picking the materials, what do we look for? Things that won't outgas, right, yeah. And adhesives, RTV, all that kind of stuff. You want to look at it so it's of space-rated material. And I don't think we use all space-rated material. So contamination degrades thermal surfaces. If you have something that outgasses, it's going to change the emissivity and the absorptivity of the surface. And thereby, you know, change the thermal balance on it. So there's two things: total mass loss and collected volatile condensable materials. And here's a chart showing some of that. And you'll see that there's stuff in there: RTV, Scotch weld, Tribond, conformal coating. What is conformal coating? Does anybody know? What's it used for? We put it on the outside of circuit boards, electronic circuit boards, And what it's for is to keep the solder from evaporating. And it does another thing. Even though it's not a very good thermal conductor, it's better than a vacuum. And it tends to conduct heat around and make a more uniform thermal surface for things. So it's good for that. Capped on there, and you can see paints, lacquers, and varnishes. And if you look at them, let's just look down the column for CVCM, and that's TML, which has the most of all those listed of the mass loss. That means actually, if you have an adhesive, you actually lose mass in the adhesive. So which one is the highest? I see 254, which is this Z93 stuff, right? So if you had a choice of those, you would probably want to pick the lowest one that would do what you wanted to with it. And the same way with the CVCM stuff. Okay, here's what happens to contamination. When you see the sun coming in and there is a shadow, is there any light in the shadow? If you walk around in the shadow of the house, the sun is not shining there, right? But it's light. Why is it light? How does the light get around there? Light travels in a straight direction, right? What's that? Reflection from other sources? What sources? What about when you see lots of things showing up that shine in the air when the sun, in the shadows? You ever seen that? What if you stir up dust? What do you see? Do you see the sun shining off of those particles? Well, what's actually happening down here, there is contaminations in the air, and the light comes in and it hits those particles, and actually that's how the light gets around in the shadow. If you're in space where you're in a vacuum and supposedly you're not contaminated, if you go around in the shadow of your satellite, you can't see anything. There's no light there. So what happens in a vacuum, when you have outgassing, it goes in a straight line. It doesn't hit anything like it would down here. If you have things coming out of your upholstery, how does it get to the windshield? It must bounce around and hit the windshield, right? But it doesn't do that in a vacuum. So what you can do, if this is where all the gas is coming from, and you've got something over here that's an instrument, you put up a shield, right? So, gassing out source, shield, it won't get there, all right? Or you could put shields to deflect it any place. So on a little satellite like a pocket cube or a CubeSat, what is the thing on the outside that you don't want the outgassing to condense on? The solar cells. Okay. Well, we're at the end of the time here. We'll finish this up on Thursday.